This is section 1.3, displacement in two dimensions. In this section, we're going to talk about different method of adding vectors, adding displacement. We need to combine vectors in order to describe the position of the vectors in two dimensions. So the knowledge about vectors and their properties is very crucial in this section. So we're going to learn a lot about how to determine the object two-dimensional displacement using different methods. For example, using a scale graph diagram, using a component method, or using a cosine or sine method. In this section, you should be able to practice using your protractor, ruler, and you need a calculator as well. So get those ready and let's continue. We're going to learn how to express the direction in a coordinate system. The coordinate system, we can use it the same way as we use it in math, as an X and Y coordinate system. However, we can use north, south, east, and west as well. So the common thing between those two coordinate systems is that they are perpendicular to each other. So if the vector is drawn in that coordinate system, you should be able to describe the vectors in two-dimensional or resolve the vector in two dimensions. And we can express it how this vector is in respect of this coordinate system. For example, here is a coordinate system, north, south, east, west. They are perpendicular to each other, and each of those quadrants have a 90-degree angle. So there is a vector A, vector B, vector C, vector D. How can we express the direction of those vectors so every one that you can tell to draw, ask to draw a vector A, should be able to draw exactly the same, no matter how you are going to describe it. So, as a matter of fact, there are 4 ways to describe that direction of the vector A. For example, if you want to start from east and you have to move toward to that direction, how many degrees you have to rotate, you have to move? It has to be 35 degrees. So you can express it east, you move toward north 35 degrees. So everybody understand you can draw a 35-degree angle 35 degrees, and then you draw a line which is a vector A. However, what about if you start from north? There's nothing wrong to start from north, but you have to say it, what is the angle? But this angle now is not 35 anymore. It is 90 minus 35. So that one actually is going to be 55. So you can express exactly the same vector, now slightly differently. North, 55, east. So those two directions with a square bracket, actually, they are mostly used in physics. But in everyday, we don't say it like open bracket, east, 35 degree, north, close bracket. We just say it as a 35 degree north of east. Or if you move 35 degree east of north. So you should be able to know all 4 of them. Not because you have to express and say it every time 4 ways a vector, but you should understand in any ways that is given to you, you should be able to draw a vector. For example, vector B. Vector B starts from south, 12 degree. So we can write it south, 12 degree toward east. However, what if we start from east? So it's a 90 degree minus 12 is 78. So we can say east, 78 degree toward south. or 12 degree east of south, or 78 degree south of east. Vector C, it is really maybe easier or maybe confusing because 45 is half of 90. So no matter where you go, where you start from, it is going to be 45 anyways. So it's going to be, if you start from south, it's going to be south 45 west. And if you start from west, it's going to be 90 minus 45, which is 45. So west 45 south. And the last one would be D. D is 80 degree from west. So you can write west and you move 80 degree toward north, or what is 90 minus 80 is 10. You start from north 10 degree toward west, or 80 degree north of west, or 10 degree west of north. We're going to focus on this part of the lesson, adding vectors graphically. When we add vectors in 2 dimensions, the vector will not always point due north, south, east, or west, or x-axis or y-axis. They can point anywhere in between. It's like any motion. So that's why we need to know how to draw a vector properly. When we add vectors, we get a resultant. So resultant vector is a vector that results from adding 2 or more vectors together. We have 2 rules to add them: tip to tail rule and parallelogram rule. Tip to tail rule is when we have 2 vectors, we can leave one vector alone, and then you slide the next vector and you place a tail of the second vector to the tip of the first vector. So in this case, you slide the tail of the E vector to the tip of the D. Then you draw vector F, which is equal to D plus E. How to draw it? It's always the same rule. If you have 2 or more vectors, it is going to be the same. You start where the first vector starts, and you draw a line, and ends where the last vector ends. Why did I say last? I said last because you can have 2, 3, or any number of vectors. As long as you place it in that tip to tail rule, that is going to be a resultant from the first start to the last end. The second one, parallelogram rule, is very useful when 2 vectors are placed at the same origin. So they have a common origin. For example, in this case, you don't need actually to slide that vector E parallel to itself. You just, from the tip of the 2 vectors, you can draw a parallel line, and when those 2 parallel lines intercept, then it is a tip of the resultant. Always the start of the vector F, which is a resultant, has to start from that origin, a common origin. So all 3 vectors, those 2 that you add up, and the vector F that is a resultant of those 2 vectors should have and must have the same origin. That is a key. Now here's a practice. So you place the tail of the second at the head or at tip of the first. That's a rule. You do that, you'll do adding vectors always correctly. So the total or a sum has to point from a tail of the first vector to a tip of the last. One more time, you have 2 vectors. Now they are not starting from same origin. Same thing. If they are not starting from same origin, you draw one vector as it is, or basically leave the vector where it is and move only one vector parallel to itself and place it the tail of the vector 2 to a tip of the vector 1. And then you can join tail of the vector 1 toward tip of the vector 2. And that will be always correct if you do follow that direction, that rule. Now, as I said, you can have more than two vectors. That's exactly the same. I mentioned that many times. If you have a vector A here, and you can place a vector B where the vector A ends, and you can place a vector C where the B ends, and then the vector total, or a sum of A plus B plus C, is a vector D that start where the vector A start and join where the vector, last vector, that in this case vector C, ends. And you will never make mistake if you follow that rule. To draw a two-dimensional vector using a scale diagram, we need to determine the reasonable scale. For example, if we need to draw a 15-meter vector, you don't have a 15-meter paper to draw it. So you have to decide what would be a reasonable scale to use in order to draw a vector in a paper, so that vector has to represent a 15-meter vector. For example, if you have a 15-meter west 35-degree north, you have to use a scale that is 1 centimeter for 5 meters. So you have to write it down. So when you draw it, you have to draw it 3 centimeters, because that length represents a magnitude of that vector, 3 centimeters, and you have multiplied by 5 is going to be 15 meters. However, you can change the scale as you like. For example, if the 3 centimeters it is too long to draw for the space that you have, you can use a different scale, like 1 centimeter is equal 10 meters. So now you can draw the same vector, but this time has to be 1.5 centimeters, because when you measure back, it's going to be 1.5 times 10 meters is going to be 15 meters. So that has to match. Now for angle, that's why you use a protractor. So angle has to match too. So what do you do? From west, you draw a line, a very light line, 35 degrees toward north. Then you measure it, that the vector in that line, 1.5 for scale 1 centimeter with 10 meters, or 3 centimeters for the scale 1 centimeter with 5 meters. Then you can draw a hard line with an arrow that represents the vector, which is 15 meters west, 35 north. Sometime you might have more than one vector to draw. So let's say that you have 540 meter vector. You can use a scale of 1 centimeter with a 100 meter, and you can draw 1 centimeter, 100 meter. That means you can draw 5.4 centimeter vector that represent 540 meter. But if you have another vector here, you have to consider that as well, because that scale that you decide has to be exactly the same for the second vector or for a total vector, because that scale has to be 1 to show the vectors proportionally. If the vector delta D1, for example, is smaller than delta D2, you draw delta D1 with that scale to show to be shorter than delta D2. Let's give you an example. If you have 540 meter delta D1 and have 700 meter delta D2, you can draw with the same scale, 1 to 100, 5.4 centimeter delta D1 and 7 centimeter for delta D2. So that scale has to be the same for the set of vectors. So that's what I said, is a scale chosen has to accommodate all vectors in diagram. Exactly the same to show proportionality. Which one vector has a bigger magnitude than the other. At the end, after finding the total displacement, you draw it, and I'm going to teach you how to draw it shortly. You need to convert the value back to the original unit. You cannot express something like this. First displacement is 540 meter. Second displacement is 700 meter. And total displacement is 400, for example. Depends on the angle, obviously. It's a 400 meter. So you cannot say that delta D total is 4 centimeter. Yes, you draw it, that is 4 centimeter. You measure it, that is 4 centimeter. But you have to convert it back to original units, which was meter. And the scale was 1 centimeter with 100 meter. So let's say that total happened to be 400. You have to say that total is, if happened to be that total is 4 centimeter in your diagram, then you have to say that total is not 4 centimeter, but is 400 meter. So in this example, the scale that I use is 1 centimeter with 100 meter, and you have to write it and follow that scale for all the vectors involved, not just one. To summarize it, to draw two-dimensional vectors using a scale diagram, you need to determine the reasonable scale for the diagram to accommodate all those vectors, to have into consideration the magnitude of all vectors. So those vectors, when you draw, has to fit to the space that you have in the paper. For example, if you have a scale 1 centimeter with 10 centimeter, that scale has to apply to all of them, including total displacement, total or resultant vector. So at the end, after finding that total displacement, you need to convert it back to the original value using the same scale. So if that total is 5 centimeter, for example, you have to say 5 centimeters, since that scale is 1 centimeter, 10 meter, now that vector has to be 50 meter. Here is one example. If you have to draw a vector delta D1 and delta D2, you know exactly that delta D1 is shorter than delta D2. And you can say that delta D1, it is east 35 north. Delta D2 is east. So the delta D total is the line that joins where the delta D1 starts toward where delta D2 ends. You join it, you measure it, and you scale it back. You convert it back to the original units. And for this, you need practice. And for this, you need to have a graph paper or any paper per se. But the graphing paper is easier because we'll make right angle triangle easier for you to draw. And another thing that I mentioned at the beginning is you need a ruler and protractor to do assignment for this chapter. We learn about vector additions, how to add vectors together using tip to tail. What about subtracting it? That's pretty much the same. The only trick here is you can do vector D is equal A plus minus vector B. So in order to subtract B from A, you add minus B to A. So you can draw A, and then you can draw minus B. Then you can follow the same rule, tip to tail. So you place vector minus B where the vector A ends, and then draw a vector resultant, which is D, or A minus B, which starts where the vector A starts and ends where the vector minus B ends. Here is a time that you have to practice in order to learn how to draw a scale graph diagram. At the beginning, I told you to get ready with a protractor, ruler, paper, graphing paper if you want, and practice. It's not about learning or reading or listening or watching. It's about practice. Okay, so a ball undergoes a displacement of delta D1 6.2 west 25 south as it approaches the wall. It bounces off with a delta D2 equal 4.8 meter west 25 north. The whole motion takes 3.7 seconds, that is the time. Determines squash ball, total displacement, and average velocity. So you don't need to calculate displacement using any math algebraic method. You have to draw it. Then when you determine displacement, average velocity is easy. You can just divide it by time and you get the average velocity. Let's start working. And if you're not ready, pause the video, get things ready, and then we can start doing things together. So the first thing, you have to determine the scale. Remember, scale, because you need to fit those vectors in a paper that you have there, the space that you have on a paper. I chose to be 1 centimeter is equal 1 meter because I can draw 6.2 centimeter and 4.8 centimeter easily on my paper here. Okay, but that's not all, because another important thing is to determine where those vectors are, in which quadrant. Because if you decide to use that coordinate system in the middle, so that means that you are starting here in the middle, you're going out and you're going outside. So that's why you need to determine in advance how to use it. So you can draw something here in outside or in a piece of paper in advance to know exactly what happened. Then next step would be draw a coordinate system. The coordinate system is exactly what it needs to be by leaving the whole space in the quadrant 3, because I know that where the vectors will be, and less on quadrant 2, because maybe that vector might go above the line, so I need a little bit space there. I don't know exactly, and maybe a little bit here in case. I'm not sure, but definitely nothing is going to be on quadrant 1. So that's the next step that I do, decide how to draw a coordinate system. After drawing the coordinate system, I need to measure the angle for vector delta D1, west 25 south. So pretty much is going to be between west and south. It's going to be somewhere here, but has to be absolutely accurate. So that's why you use a protractor. So then you can actually count 10 degree, 20, 25. So I put a dot here and I draw a thin line So I can have a line now to measure later. So I measure the angle, and that is a very important step. Next step would be measure the length of the vector itself. So I use a ruler to measure 6.2 centimeter. So make sure that it's very accurate because 1 millimeter is a lot. So 6.2, and then I draw and label it. I draw. So how can we add a next vector? Remember tip to tail? So the second vector has to start where the tip of the first vector is. So that's why we build a new coordinate system exactly where the tip of the first vector is. Remember that, I warn you, this is a common mistake that people do by just not drawing that second coordinate system. And they just draw a 25-degree, for example, based on the delta D1, and that will be wrong. So you draw a second coordinate system where that tip of the vector 1 is, because there is going to start a vector delta D2, which is going to measure between west and north. So it's going to be something in that direction, but has to be accurate. So that's why you need a protractor. Then you count. You count from 0 here to 10, 20, 25. You put a dot here, and then you can draw a line. And that's how you measure 25-degree from west toward north. Next step would be similar to what we did at displacement delta D1. You measure it and draw that vector and label it. Now you are ready for a final step, and final step is how the total displacement is. It starts where the first vector starts and ends where the last ends. So you have to draw a line here to join those 2 points. So just start from where the first started toward where the last end. And then you draw a vector, and then you measure the length. That is exactly what you do. You measure the length, which is approximately 10. That's what I'm saying. You have to draw it as big as possible to see the difference, because 9.9 and 10.1 is a big difference. So measure the length and convert it back to the unit that you started with. Remember, 1 centimeter is equal to 1 meter. So now we have 10 centimeter. So we cannot say it's a 10 centimeter as a total displacement. You have to convert it back to the real units. So by using the same scale. So 10 centimeter, if you convert it back, would be converted 10 meter. So then you can write it exactly what it should be. Total displacement is equal to 10 meter, not 10 centimeter, 10 meter. So it is a vector and you need a direction. So that's why you still use a protractor to measure the angle. In this case, in this example, the angle is so small. In my view, this angle is 3 degrees. So I can write it. I can write it. It is between west toward south. So I can write it as west 3 degrees south. And then next, I can write the answer as a whole thing. I can write the answer like delta D total is equal to 10 meter, not 10 centimeter, 10 meter, west 3 degrees south. And the final step would be that piece of cake. Just you do have displacement already now. You divide it by time. Then you have 10 meter west, 3 degrees south divided by 3.7 is equal to 2.7 meter per second. But you have to do it with a direction because it's a vector quantity. Displacement is a vector quantity, need a direction. Velocity is a vector quantity, need a direction. So 2.7 meter per second west, 3 degree south, and that will be an answer. So in this way, we concluded scale graph diagram method, the first method of adding displacement in 2 dimension. So on the bottom of this page, there is an answer for this. So it's a 10 meter west, 3 degree south. That is total displacement. However, we're going to use the same problem with the 2 other methods, and we're going to compare it. How close, how accurate can we be? Which method is more accurate? What are downside of other methods? So we're going to talk about this after we learn one method at a time. We are done with the scale graph diagram method. Knowledge about the vectors and their properties is very important because it's going to help you not only on this chapter but for other concepts like forces. We need to combine vectors in order to describe the position of the object in 2 dimensions. You'll determine the object 2-dimensional displacement using a different method, and one you already have learned. It's a scale graph diagram method. Scale graph diagram method is very important. It has the application on a design, architecture, designing the map of the city, etc. However, it has its own limitation and sometimes it's very difficult and not accurate. The component method is very important, and this one actually is connected to a trigonometry. It's about right angle triangle with a hypotenuse, opposite, adjacent, and angle. So if you have those properties of right angle triangle, you can combine those properties to find what is missing component. For example, if you want to find hypotenuse and you do have opposite and adjacent, using a Pythagorean theorem, square root of opposite square plus adjacent square equals hypotenuse. Or you need to find angle theta using a tan -1 of opposite over adjacent. Or if you want to find opposite and you have hypotenuse and angle theta, you can use formula of opposite is equal hypotenuse sine theta and adjacent is equal hypotenuse cosine theta. However, the problem here is how to remember, how to know 100% which component to use, sine or cosine, for a side, which side, how to determine. I've seen many people make that mistake, and if you make a mistake, it's going to be 100% mistake, because if you use cosine instead of sine, you're going to use sine instead of cosine on other one. So how can we get 100% accurately, the answer accurate all the time? Yes, here is a SOHCAHTOA, the method that widely used in a trigonometry in North America. So it's a sine is equal opposite over hypotenuse, that's why SOH. And cosine is equal adjacent over hypotenuse, and tan is equal opposite over adjacent. So those three SOHCAHTOA are, those three equations are important. However, I still see people making that mistake. Instead of using sine, they use cosine or vice versa. The best way to remember is you use sine in front for the side in front of angle theta. So the angle theta is looking at that side that you can use sine. Think about this as it's looking toward that front side. So then what you see when you're looking from that angle point of view, you see a side that you can find it using sine. See sine. If that helps, that will be great. So beside the angle is cosine that you cannot see, but you're looking at the side that is in front of you. Think about this, you go to a theater. What you see when you go to a theater, you see a screen that is in front of you. You don't go to a theater to see chairs or floor. That might be something that will help you. The side on the front of the angle is the one that you can use sine, because that's how you see it if you are in that angle position. I think that might help, because that is very important to get those components right. Because if you don't get those components right, everything after is going to be affected by that mistake that you did, and everything after is going to be messed up, wrong. So I hope that will work, because that is very important. Very important. This slide is very important for this section. Now we see a transformation of that triangle with a hypotenuse, an opposite and adjacent, to a vector. It's not a big difference, isn't it? Pretty much is the same. Now we have x and y coordinates. And now we're going to just talk about not a side of the triangle, but a component of that vector. So this vector can be replaced by delta d, or velocity, or forces in the future. Everything that applies on this vector applies on a displacement, velocity, acceleration, or forces, because all of them are vector quantity. So I label that hypotenuse as a vector, v. Now, remember that we have the angle theta, and in front of the angle is the side that you can use sine. So in order to find the y component of this vector, you can use Vy is equal to V sine theta. And beside that angle is x component, that is V cosine theta. Remember, it is not about y or x, it's about what is in front of angle and what is beside the angle. That use sine or cosine. And the rest is the same. So if you have two components, you can use a Pythagorean theorem, and you can find the vector, the magnitude of the vector, or you can calculate that angle, that vector form with the x-axis in this case. So it is about a component on an x and a component on a y-axis. And it's very important to know when to use sine and when to use cosine. In a vector quantities, direction is important. And the sign of the vector component is important too. But those depend on where that vector actually is located in regards to angle theta. So angle theta is measured counterclockwise from x-axis. So from here at the 0, it's a 0 degree, and it goes to a 90 degree on a positive direction of the y-axis, and that goes to a 180 degree on a negative direction of x-axis, and goes 270 degree on a negative direction of the y-axis, and goes back to 360 or /0 to the x-axis. So we should know now that in the first quadrant this is 0 to 90, second quadrant is 90 to 180, third quadrant 180 to 270, and fourth quadrant 270 to 360 or to 0. Now on the first quadrant, take a look. Y-axis has a positive up as a traditional, and x-axis has a positive on the right. The component of vector A has positive ax and positive ay. In the second quadrant, when it's between 90 and 180, you have a negative ax and positive ay. On the third quadrant, you have negative ax and negative ay. So both of them are negative. And on a fourth quadrant, you have a negative y but positive x. Here is an example. In what range the vector that has negative x component and positive y component, negative x component and positive y component, and we're talking about A, which is in the first quadrant, B, that is in the second, C, that is in the third quadrant, or D, that is in the fourth quadrant. If you said B, you're right. We're going to start to learn about resolving a vector into component. We can use different words for that: resolve, split, separate. It's the same thing. So we can resolve a vector into component that must be perpendicular to each other, and they lie along either x-axis or y-axis, and name of those components is taken by those two axes. So that's why we say x component of the vector and y component of that vector, because x component is along x-axis and y component is perpendicular to x-axis. That means along y-axis. Here is an example. And by the way, not necessarily that you have to say always x and y, but sometimes we interchange between north, south, east, west, and x and y. And that is going to be common most of the time. Let's say that you have an example of a displacement 5 kilometer east, 37 north. Now we have to find two components of that displacement, x and y component. And x component is always along the horizontal one, which is east direction this time. And y is always perpendicular or vertical, which in this case is north. So using that SOHCAHTOA, or using anything that it works for you, either like a looking at from the angle, then you can use sine for y component, which is delta dy is equal delta d sine theta, and beside that angle you can use delta dx is equal delta d cosine theta. I want you to pause the video and right now and try to find those two components, delta dy and delta dx. Remember, it's a 5 kilometer sine 37 and 5 kilometer cosine 37. And where those sine and cosine came from, remember that SOHCAHTOA So cosine theta is adjacent over hypotenuse. Sine theta is opposite over hypotenuse. So, or in this case, we have cosine theta is equal delta dx divided by delta d, which is hypotenuse, and sine theta is delta dy over delta d. If you found that is a 3 kilometer north and 4 kilometers east, you are right. Now, I want to draw your attention to this diagram on a lower right. If you see that there is an angle there, there's a vector with angle along the y-axis. So on the left, you have an angle that is forming, the vector is forming with x-axis. So that's why this y component is the one that you can use sine. Now the angle here is making, that's angle that vector is making with a y-axis. So in the front of this phi angle, it is x component now. So x component is equal c sine theta. So now for x component, you are using sine, not cosine as you used before. So as you see, using sine or cosine, and that's how many people get confused, does not depend on x or y. It depends on angle. So if you use sine, has to be in front of the angle, has to be opposite. And if you want to use cosine, have to be beside that angle. So that has to be adjacent. So that's why in this example, you have a different arrangement of the x component and y component. Sometime you may have a vector, and in order to find the component of that graph, you just simply read the values on the graph. For example, if the vector v and you're being asked to calculate what is component x and component y of this vector, you just simply read from the graph. So x component of that vector is -6, because that is direction of the x component, and +4, because that is direction of the y component. And you can go even further by looking at that, by having those two components, 4 and -6, you can calculate the magnitude of velocity, which is square root of x component square plus y component square. And you can use tan -1, opposite over adjacent, in order to find angle theta that this vector form with x-axis in this case. So I want you to pause the video and make that calculation by having x component -6, y component +4, find the magnitude of the vector v and a direction. If your answer is 7.2 meters per second and angle is 33.7, you are correct. Now here is another practice. Now this time is a reverse. You do have magnitude of the vector r, and you do have angle theta, which is 25 degrees. I want you to calculate rx and ry. So x component of r and y component of r. So you pause the video, and I want you to calculate what is rx equal to and what is ry equals to. If you did get this result, Rx is equal R cosine 25 because it's beside the angle, is 1.5 times cosine 25 degree is 0.906. You don't have to write this, you just do that in your calculator. And that is equal to 1.36 meter. That is positive. And y component is a positive 2 because in, vector r is in the first quadrant. That is r sine 25 degree. That is equal to 0.634. Now the next one is, what if you have those two? So you have Rx and Ry. How to go reverse and find the magnitude of R and the angle of that vector that is forming with x-axis. I want you to pause the video and try to practice finding the magnitude of R and finding the angle. If you get this result, R is equal to 1.5 and angle theta is almost 25 degrees, using those calculations, you are correct. What we learned so far is an introduction of what we want to do. We want to add two or more displacement vectors together to find the total displacement. For example, if you want to find displacement of vector A and vector B, we resolve this vector into its own x and y component. We have ax and ay and bx and by. Then next step is going to be adding x component and y component separately. So we can find Cx is equal ax plus bx and Cy is equal ay plus by. And then the last step would be using a Pythagorean theorem to find vector c, which is the square root of cx squared plus cy squared. Same way as we use vector a and b to add and get the vector c as a total of a and b using component x together and y together, and using a Pythagorean theorem to find magnitude of c, and tan negative 1 to find angle of the c. We can do the same thing now, but there's a real delta d1 and delta d2. We can first we can resolve this delta d1 in two components as a delta d1x and delta d1y, and we do the same thing for delta d2, so delta d2x and delta d2y, and then you can add x components together, get delta d total x as delta d1x plus delta d2x plus any x component if we have more than two vectors. And the same way we do for y component, delta d2 total y is equal delta d1y plus delta d2y plus any delta d3y or something. Then, using a Pythagorean theorem to find delta d total, square root of delta d total x squared plus delta d total y squared, and use a tan negative 1 to find the angle between x-axis and delta d total, which is tan negative 1 of delta d total y divided by delta t total x. Here is a graphical summary of adding two vectors using component method. We already did many examples, but let's review it. You can add two or more vectors. So you do the same thing for each of them. You resolve those vectors into component x and y, and then you can add all x components together and you add all y components together. Remember, you have to be careful to take into consideration sine of those vectors. And then after you're getting total on x and total on a y, you draw that. Drawing is very important because it gives you an idea what is expected from that calculation. Then you can use Pythagorean theorem to get total vector and direction using tan -1, and then you state the result. You answer it with magnitude and direction. Okay, now it's a real thing. It's a practice. What I want you is to get a piece of paper, get a pencil, get a calculator, and then do it with me. A ball undergoes a displacement of delta D1, 6.2 meter west, 25 south. As it approaches a wall, it bounces off with a delta D2, 4.8 meter west, 25 degree north. The whole action takes 3.7 seconds. Determine the ball total displacement and average velocity. If you recognize this, it is exactly what we did using a scale graph diagram. So now we are going to use component method. What we do is draw delta D1 and delta D2 in the same set of axes. Yes, you can draw it in a different set of axes if you want, but it is helpful to draw it in a same set of axes because you'll see the total, you'll see it is helpful. But anyways, it's up to you to do whatever you want as long as you do it correctly. So draw it proportionally. Two vectors, label it, label the angle. And the first thing that you can do after drawing those two displacement, you can draw and calculate their component. So make sure you calculate x component and y component for each of them. Now, labeling is very important because it is not the same as you're labeling delta D1 and delta D1x and delta D1y. It's very important. So x component is along the x-axis, obviously, and y component is along y-axis. Do the same thing for delta D2. Okay, and then calculate delta D1x is equal to delta D1 cosine 25 degree, y cosine, because delta D1x is adjacent for angle 25. Okay, it's beside the angle. So delta D1y is in front of that angle. That's why we use sine. But both, since the delta D1, and you should know that by now, is in a third quadrant, both x and y component has to be negative. For delta D2, it is in a second quadrant. Is it clearly delta D2y is positive and delta D2x is negative. So that's what we do. Calculate delta D2x and delta D2y, which delta D2x is adjacent for this angle 25, happen to be both 25, and delta D2y is in the front of that angle, is facing that angle. So that means it's opposite. That means you are using sine because you can see that side. If you put an eye at this angle, you can see it. Whatever works for you, doesn't matter as long as you do it correctly. So y is positive, delta D2x is negative. Then what do we do? Next step is you add those components together, but remember, there are some positives, some negatives. You have to make sure you don't ignore those signs. Signs are very important. For delta total x, you can add x's together, x component together, So delta d1x is negative, and delta d2x is negative also. So obviously sum is going to be negative. And for delta d total y, that delta d1y was negative, and the other one was positive. So they are very close together. That's why the difference between those two is negative, but very small number. Next thing is very, very recommended to draw those vectors. So when you have those two vectors, so total, delta d total x and d total y happen to be both negative. So that's why I draw an axis here only with a third quadrant, because we're not using second, we're not using first, we're not using fourth quadrant, we're using only third quadrant. So that's why I draw those. Then it is very recommended to draw those, because that gives you an idea, the magnitude and the direction. Even if you make a mistake when you did those calculations, or the mistakes when you are going to do the calculation in later, then that drawing will give you an idea what is expected direction and magnitude of those two components of the vector delta d total. So delta d total x and delta d total y, you can draw those proportionally. You don't have to measure it, but obviously we are talking about delta d total x is almost 10 centimeter, and delta d total y is almost half. So obviously that is going to be a huge difference in a length when we draw it. So it gives you an idea that angle is small. It gives you an idea. And it gives you an idea that the hypotenuse is not really that big compared to 9.94, that is x, because the y component is small, so it's not going to increase that much. So those things are very important for you to figure out how to get it right, and you have an estimate. The best thing actually for you to solve problems is to have that estimate skill. So you should be able to estimate things. Again, so you can use a Pythagorean theorem to find magnitude of delta total, delta t. So it's a square root of delta tx squared plus delta dt y squared. And then it's a 9.96, which doesn't really change much from 994. Calculate the angle, and the angle is going to be very small. Obviously, it's 0.59 divided by 9.94, and you do that in calculator to test it, your skills of using your own calculator, and that will be 3.4. So after getting those two, you can write an answer which is going to be a total. Please write the total with a magnitude and a direction. Now, remember that this, how come that how can we figure out the direction? The same way, so it's a west, which is like a negative for x-axis, and south, which is negative for y-axis. So it is between west 3.4 towards south. Okay, and then last step would be a piece of cake. You just divide delta d total with time. It's a 9.96 divided by 3.7. Direction is the same. So it's a west 3.4 degree south. So the answer would be 2.69 meter per second, west 3.4 south. So when we have those values, answers for delta d total, for angle, and for velocity, we have a confidence that those values are going to be much closer to reality, more accurate compared to the values that we did when we use drawing and measuring and scaling. Obviously, that's why this method is accurate, more accurate. And you can add as many vectors as you want. The same as a scale graph diagram, you can add as many vectors as you want. The only thing is that this method is more accurate. Now let's compare those values with the values that we actually had using the scale graph diagram. This is a third method of adding two vectors in two dimensions. This is a trigonometry method. Only work when adding two vectors at a time. This is downside of it. However, it's very accurate compared to a scale graph diagram, and obviously it is comparable with component method. For example, if delta D1 is equal to 140 meter east, 35 north, and delta D2 is 200 meter east, how can you get delta D total using cosine and sine law? Using cosine law first, we can calculate delta D total, which is delta D total square is equal to delta D1 square plus delta D2 square minus 2 delta D1, delta D2 cosine theta 2. So cosine theta 2 is angle between two vectors that we are adding up. Make sure that delta D2 is angle between vectors that you are adding up, or in the front of delta D total. Okay, so is delta theta 2 is 145, so delta D total is square root of 140 square plus 200 square minus 2 times 140 times 200 times cosine 145 degree. Where this 145 degree came from? You know that's a 180 degree for a wide flat angle. So 180 minus 35, that is given already. This angle here is given. You calculate theta 2 is 180 minus 35 is 145. You're going to do this calculation all the time. So this angle theta 2 is not given. You'll figure out, but it's easy to figure it out. So delta D total, after you did those calculations in your calculator, is 324.8. You try it yourself and see if we got it right. Now, to get an angle, the angle between the total vector and the horizontal axis, x-axis or east axis in this case, is theta. How to find it? We know that this angle here is 35 degrees because it's given. Now we are going to look for the angle in that triangle using sine law. Then we can say this angle here, theta, is equal 35 minus theta 3. So theta 3 is in the front of delta D2. So we know sine of this angle over the side is equal to sine of this angle over this side. So that means A divided by sine A is equal to B, side B, over sine of the angle B equals C divided by sine of angle C that is in the front of that side C. So if you don't remember cosine and sine law, just go in a math textbook and just refresh it. But that's what it is. And cosine law, by the way, I think that you might know by now, is c squared is equal a squared plus b squared minus 2ab cosine c. You can consult with math knowledge, but that would be it. So we already calculated delta D total, and we can calculate now sine theta 3 in order to find theta 3. So sine theta 3 is delta D2 sine theta 2 over delta D total. So it's a 200 meter times sine 145 divided by 324.8. Then we're looking for theta, not sine. Theta is sine -1 of 0.616, which we divided 200 with 324.8. Sine 145, that is equal to 20.69 degree. You can try your calculator and do it yourself. But we're not looking for theta 3. We're looking for theta. But I mentioned that it's 35 minus theta 3 is equal to this theta. That's what we do. 35 minus 20.69 is 14.3. And the final step is you can write the sentence. You can write the answer. Delta D total is equal 324.8 meter east, 14.3 degree toward north. And that would be an answer. Okay, we're going to take the same problem that we solved using scale graph diagram, using component method. Now we're going to use the same problem and we're going to solve it using cosine and sine law method. So what we had a delta D1 6.2 west, 25 south, delta D2 4.8 west, 25 north, and find delta D total. So delta D total is equal to delta D1 square plus delta D2 square minus 2 delta D1 delta D2 cosine theta, and we square root it. Now, in order to do it, you need theta 3. So theta 3 is that angle between two displacement that we're going to add. Always is between two displacement that we add. Now, this one actually is 180. This is 25 because it's given. This would be 25 because this one is 25. So it happened to be both 25. Now, this is 180 minus 25 equals 130. So if we get this, we can do everything now. Everything is known. 6.2 square, 4.8 square, minus 2, 6.2 times 4.8 cosine 130, and we square root it. Then we get 9.987 meter, so close to 10. And we did a good job with that scale graph diagram. Very close, very close. And angle was 3. With other method was 3.4. Let's see with this method. Now, use a sine law in order to calculate theta 2, and then we can calculate theta. So sine theta 3 over delta D total is equal to sine theta 2 divided by delta D2. So we solve for sine theta 2, which is delta D2 sine theta 3 over delta D total. We plug those numbers. We have all known values. And then we can find theta, which is tan -1 of what is on 0.48 is 4.8 divided by 9.987. Sine 130 degree will give you 21.6. Now, we are not looking for theta 2, right? We're looking for theta. But theta is equal 25 minus theta 2, which is 21.6, which is 3.4. That is amazing. Very, very accurate using the same with component method. Then delta D total is 9.99 meter west, 3.4 degree south. And that will be entire lesson. We learned all three methods. We proved it. All three methods will give us very, very close result. So I hope you enjoy it. Until next time, have a good one.